Welcome to our final class. So congratulations. We almost survived, just about there to the end. So the plan for today was just to talk about the exam. So we've got our last exam on Monday. And just to make sure we're clear what the content of that exam is, that is going to cover Laplace transforms, chapter 6. So basically just the last homework that you just completed. So that would be sections 6.1 and 6.2 in the reading materials. And so the main points here, just to bullet them out, would be the definition of Laplace transform, so you will be expected to calculate, derive some Laplace transforms from the definition. Using the tables and the properties. And I'll just say that will be provided with the exam. So you'll have the same sort of table and properties bulleted out that you've had in the worksheets. We did derive some of these properties. Some of the proofs were beyond maybe the scope of the class, and we cut a little bit of corners, but in particular, the properties that we were able to work through were the two linear ones. Why can we split up sums, and why can we pull out constant multiples? And then after we got comfortable calculating Laplace transforms of things, then we went in the opposite direction and did inverse Laplace transforms. And then finally, solving diffie q's. And again, what's important to note here is that the differential equations that we can solve with this method, right, they have to be initial value problems. If we don't have initial conditions, then we wouldn't be able to solve a differential equation using this method. So that's the scope of the exam. It's a little bit more narrow than, say, previous exams, and that's why it's not worth as much credit as the other exams. But I would say the material is probably a little bit trickier, a little bit more abstract. So there's a trade-off with that. So I would just caution anybody from doing the what if analysis in Canvas and saying like, oh, I only need to get this in order to get that sort of grade. I would just encourage you all to do as good as you possibly can, regardless of what grade you might need to do. So yeah, so our exam is Monday, December 7th. And it's going to go from, it's scheduled from 11 to 1. It should take about as much time as the other exam. So I'm going to say you should plan to go from at most 11 to 12:30. So an hour and a half should be enough time for that.
Are we going to do a Zoom meeting with that? Because on your little link for Zooms, this was our last Zoom
yeah,
meeting, so.
I just edited that. I noticed that as I was opening up this one. So I now the last scheduled date for this Zoom is Monday. It might say that it ends at 12:15, but that doesn't matter. But yeah, it'll be the same Zoom address. I'm not going to change that up on you. Yeah. Yeah, and so it'll be a little bit of multiple choice like the previous one, and then some written answers. So we can take a look at some particular examples if you like, but are there any kind of more general questions about the exam, how it's going to be administered, or anything like that? Your grade information is up to date in Canvas, except for the homework that you guys submitted on Monday night. I did put solutions to that assignment up this morning, so you can check your work on those. We can talk about some of them right now if you have questions on problems from the last homework. So your lowest homework score should be dropped before your homework average is calculated. And your lowest reading quiz should also be dropped before that was calculated. Yeah, and then we've got this exam. Are there any other kind of questions about how this exam's gonna go? Okay. Sorry, yeah, there was a question. Or not. Was there a question, Christina?
Yeah, is there multiple choice for this one too? Is it that same format?
There's going to be a section to start off with some multiple choice, and then there'll be some written answers.
Okay.
Yeah, and I should say one thing, yeah, this is important to note. On the review sheet, the first couple of problems are like, is this separable? Is this linear? That technically was not on in chapter 6, but I think that's some really important stuff that I would like you to review and take away out from this class. And so I would definitely kind of review what it means to be linear versus separable. And it's possible to be both linear and separable, or neither linear and separable, as far as it pertains say to first order differential equations. So there were there's some problems on the practice, and there were some multiple choice questions that you did on reading quiz. And I would say check out the multiple choice questions from exam 1. There were some of those, and that was those questions were some of the more missed multiple choice questions. So I do think it would be worth reviewing some of those as well. Let's see, something came into, whoa. Okay, so there were a couple questions that came into the chat, so I can get to those. Anything else? Okay, so I want to just go back and mention something that we kind of glanced over last class. So last class we did one of these, we solved the differential equation where we had like these t's in front. And so when we did that, we needed to use that property of what happens when we take the Laplace transform of t times something. And that's where these derivatives came from. And then we got to the point where we had a first order linear differential equation for y, capital Y. And so we were able to solve that using integrating factors because it was linear. And when we solved for y, we got this over here. And then, so we had this arbitrary constant, and we were able to figure out what this arbitrary constant was from the initial conditions that we had. There's one that we didn't do, which was E. I did put the solutions to this one up. And there's something different about this one, in that it's pretty similar. We solve for y of s. That means we've got some linear differential equation for y. We solve that using the integrating factor. It's a little bit more complicated here, but we can solve it. And then we get to a point down here where I've done my integrating factor. I've now solved for ys, and I'm about to take the inverse Laplace transform. I don't know we've never seen anything like this in our Laplace transforms, right? As far as like what comes out of a Laplace transform. I wouldn't know how to do the inverse Laplace transform of an exponential because we didn't see any exponentials in our table of common Laplace transforms. And so one property that we haven't discussed about Laplace transforms is that they all need to satisfy this property that the limit as s goes to infinity of the Laplace transform should be 0, has to be 0. So for this problem over here, we get this Laplace transform, and in order for this limit to approach 0 as s goes to infinity, this exponential term blows up as s gets large. So the only way this limit is going to head to 0 is if this c term is equal to 0. So for this Laplace transform to be defined, c has to be 0. So this term goes away over here, and the only thing that's left over is 3 over s squared, and then we can do the inverse of that. And that's something that's pretty similar to what's going to happen in the very last problem on the review sheet for this exam. So just keep that in mind. Any questions about that? So like we talked about last time, I did time myself. I think it took us about 30 minutes to do this problem over here. Definitely be sure to practice some of this. This would probably be like the hardest sort of problem that you might see on the exam, where you need to solve one of these where it's got t's in here. And so with that in mind, be sure you're familiar with that property about taking Laplace transform of t to some power times something, as well as just be sure that you can review this integrating factor method since that comes up in these. Yeah, Abraham.
Say, like, maybe not for this class, but if it's a t squared, we'll have to take it twice, and then we'll have to take the derivative of s of a Laplace transform twice, and then we'll get probably 2 derivatives of Laplace. So then will we get a second derivative basically? And how would we ever solve something like that? Because we started with a double derivative kind of problem, and now we have another one.
Yeah, so let's say you had something like this. You know, after you do this stuff, you had something like that, then right, these terms that don't have the t's in it, we would just do them the same way. But for this one, yeah, now this would look like -1 squared, since the power of t is 2 here. That's right, we would want to take the second derivative of the Laplace transform of y prime, or excuse me, y double prime in this case. So you would have something like this, and that's right. And so when you take the second derivative of this, first you would take the first derivative, obviously. So we use the product rule on that. And then that would give us that if we take the derivative with respect to s. And then we would need to go again. So we would get 2f of s plus 2s. I don't know why I have f's here. I guess these should be y's, right? Oops, not that one. Yeah. Sorry. We use capital Y for the Laplace transform of lower y. So yeah, so here you would take the derivative again, and you're going to get some second derivatives. That's right. And so on. And so after you group all your terms, if this were the case, then you would have some stuff times that, some stuff times that, plus some stuff times that. You'll get a second order differential equation. And then you'd have to look at it. Maybe it's easier to solve than the initial one that you started with. Maybe, maybe not. Yeah. So as far as that goes, yeah, you should expect to get a second order differential equation. Could you solve it? We have talked about some techniques for solving some second order differential equations. You won't see something like that on the exam. Okay. So I'm just keeping track. Some people are chatting in some things. So let's see, there was a question about, so for homework 9, question number 5, which was kind of using the properties to evaluate some Laplace transforms. And there's also a question about, a couple people asked about 7b. Okay, and those seem to be popular ones. I don't know how much time we'll have. There was some questions about exam 3 review, number 6, and number 8C. Okay, I don't think we're gonna get to that one, but whatever we don't get to, happy to talk about over email if people have some questions. But these were the ones that people asked for. So let me start with question 5 from homework 9. Let's see. And I've got my solutions over here. These are posted up online. So for those that may not recall, this was question number 5. So the idea is, here's something that we haven't seen in our table, namely, how do we do this? I don't know if I don't know if you guys get dizzy when I scroll through this quickly. I just want to point out one thing, and that is, since we talked about this property, that as s goes to infinity, the Laplace transform of a function should go to 0. You can see that's true for all of these cases over here. And that should be true in general. But we don't have a square root of t. So when we're using this, this only applies for positive integers. So in question 5, here we are. So here's what we know. We've got f of t. We know that the Laplace transform of that function is this weird square root of pi over 2 times s to the 3 halves. So we want to calculate different Laplace transforms. So in part A, it asks us to do this. I don't think this was as big of a point of confusion. I did look through your exams, your homeworks just quickly to see if we should talk about some of these things. And so here's property L3. And so be sure that when you're doing this on your exam, that you are justifying what property you're using as you're working through your work. But were there questions about part A? Okay. Seems not. So in part B, the question was, we wanted to calculate the Laplace transform of t to the 5 halves. And so the idea here is, well, how can we use properties and the fact that we know what the Laplace transform of the square root of t is? And the idea here is that I could write t to the 5 halves as t squared times t to the 1/2. So if I want to calculate the Laplace transform of t to the 5/2, it's the same thing as taking the Laplace transform of t squared times the function f of t, which was square root of t. And so this is where you would use that -1 to the nth power times the nth derivative of the Laplace transform of f of t. And so we have a power of 2 over here. So the sign doesn't change, but we need to take 2 derivatives of this. And so taking 2 derivatives, you would get the Laplace transform of that one. Any questions? Okay, if not, then in part C, we can't quite do the same property. So C was asking us to do the Laplace transform of 1 over the square root of t. And you might try and do the same sort of idea as in B, namely think about, well, what would I need to multiply t to the 1/2 by in order to get 1 over the square root of t, which is t to the -1/2. And you might think, okay, well, that would do the trick. However, that property that we have with multiplying by powers of t only works if the power is positive, integer. So we can't use the t property down here, but we can use the fact that there is a relation between t to the 1/2 and t to the -1/2 that we could get by the derivative. So if we were to take the derivative of f, okay, where f is t to the 1/2, we get 1/2 t to the -1/2. So we get 1/2 times the function that we would like to take the Laplace transform of. So in other words, I can write 1 over the square root of t as 2 times the derivative of the square of t to the 1/2 power. And so that's kind of the key here. So the key in B was realizing this could be written as t to a positive integer times t to the 1/2. And kind of the key thing here is that the relation between 1 over the square root of t and t to the 1/2 is through the derivative. So if I want to calculate the Laplace transform of 1 over the square root of t, that's equal to the Laplace transform of 2 times the derivative of f. We can pull the 2 out, and now we have a property that says if I know what the Laplace transform of f is, then we can figure out what the Laplace transform of f prime is. And that's this property over here. So we would get the 2 out in front, and then the Laplace transform of f prime would be s times capital F of s, Laplace transform of the original function minus f of 0. And then we could evaluate f of 0 by plugging in 0 into the original function. Square root of 0 is 0. And then for this one, we just get s times the Laplace transform of square root. So this 2 and this 2 cancel. I've got an s over s to the 3/2. So I just simplified that as square root pi over the square root of s. Okay, does that help answer questions about that one? Nobody has asked about this, but I did just quickly scroll through your homeworks, this being question 3. And so I do want to point out that I did observe some mistakes from some people on this one. So this was a question that was asking us to calculate the Laplace transform of a piecewise function. For those that don't necessarily have the assignment open, it was this function over here. in question 3. And so when you're doing this Laplace transform, you don't get a piecewise function back. So what I noticed, what some people did is they said, okay, if t goes from, or if s goes from 0 to 4, then we're just going to take the Laplace transform of this. And if s is bigger than 4, then we're going to take the Laplace transform of that. So that's not the correct way to do this. You still have one, you're only going to set up one integral. It's just you need to rearrange the limits of your integral so that, oh, what happened? Did that just happen? I don't know. Okay, good. Yeah, so in 3, we're looking at this one over here. It just means that when t went from 0 to 4, the function f was defined as 2t. So I've got an integral from 0 to 4 of e to the minus st times 2t. And then when t goes from 4 on up toward forever, the function is defined as 8. So I have 2 integrals where the limits are set up differently, but then we just go about it the same way. So in the end, we're just going to get one function for the Laplace transform of this. And you want to be careful about when you're evaluating these integrals, you know, we want to plug in 0, we want to plug in 4, we want to plug in these limits carefully. So just watch out for that. I would say for those that were a little bit unsure how to do this, go back and check your work and try and see if you made any errors on that one.
In your work right here, you have 8s and then you plus 8s at the very end, and then it turns into plus 8s e to the negative 4s. And then you cancel them out. But I thought it was supposed to just stay as 8s because that represents the
sorry, I forgot this over here. So this comes from this term over here.
Oh, yeah.
Okay.
Okay.
Yeah, thank you. You're right. I did forget to put that there. But then it disappeared over here and then reappeared back down
And
here.
that's because we take it from 4 to infinity, not from 0 to infinity.
That's right. That's right.
Gotcha.
Mm-hmm. Yeah. So yeah, this limit, as long as s is bigger than 0, that one's going to go to 0. But over here, this came from plugging 4 into that. That's right. Because the lower limit of that integral is 4. Yep. So the question was, someone asked, will we have a piecewise function on the exam? Possibly. I would definitely practice that. Yeah, that's good to review. We did one of those together on one of the worksheets as well. I think the worksheet 20, you can check that one out as well. Okay. And I'm trying to remember what were some of the other questions people wanted to talk about. Did I lose them? Ah, there they were. Okay, so yeah, so that was this one over here. Okay, then there was 7B, and then we can take a look at some of the questions from exam 3. Okay, so in 7B, here was the problem. And so it was, okay, we wanted to solve all of that. So kind of step 1 of the process is take the Laplace transform of both sides and solve for y of s. So I'll kind of, I don't know where in this process people might have had questions. So kind of after step 2, you would solve for y of s and get to this point over here. So for those that had some questions, were there any questions about this part of the process? Okay. So now we've got this fraction, and the denominator of it factors very nicely into a bunch of linear pieces. We have 2 of them that have repeated roots. So when you have repeated roots, like this one, we need to have one factor for each power of that root. So if it comes to the second power, then we're going to have 2 terms, one that's just over s to the first power, and then we'd have another one that was s squared. So we did talk about this kind of special case of partial fraction decomposition last time, and here's where it comes up. And then we have the same thing with s plus 2, and so that's why we have 2 of these. And then the factor s minus 2, that had multiplicity 1, so we only needed to include 1 of those. And when you have this special case of a repeated root, one thing to be careful about is that normally if I have a quadratic term down here, the numerators should be 1 degree less. So when I have an s minus 2, I have 1 degree less, a constant. For quadratics, we technically, you might think, well, shouldn't we have like a ds plus e over here? Normally we should, but this is kind of a special case when we have repeated roots that we don't need to have this linear term. So I'll just say, if you decide to include this extra coefficient, it won't cause you an incorrect answer. You'll just find that d should be 0. You'll just add kind of more undetermined coefficients into the analysis that aren't necessarily needed. So you can save yourself some extra letters by just saying, well, this is the special case where we just need a constant on top here. And so then it's just straight up algebra from that point, that I don't think, you know, it's the best use of our time to kind of go through the details of the algebra, but I can just kind of outline how that would look. So what you want to do is you want to put all of these things over a common denominator, right? Which is this stuff over here. So then you think, well, what would I have to multiply a by in order to get it over the common denominator? Well, I needed to multiply this denominator by s times s plus 2 squared times s minus 2. So all of this stuff over here is a times s plus 2 squared times s minus 2, right? So I would need to multiply the top and the bottom of this piece over here by all of this. So multiplying the bottom by that gives me the right denominator, and all of this stuff over here came from expanding all of this out that I'm not gonna kind of do right now, but that's where this came from. And it's the same idea. For this one over here, we now have an s squared in the bottom, so that fraction just gets multiplied by s plus 2 squared times s minus 2 on the top and on the bottom. And so that would give me the common denominator over here, and that's where all of this stuff comes from. So each of these things over here comes from multiplying each of these fractions by the appropriate thing to put it over this common denominator. So yeah, there's lots of areas to make mistakes on these. I'm aware of that, so be careful. And then once you've put it over a common denominator, then you start to group all of your like terms. So for example, for the s to the 4th terms, we've got this one, we've got this one, and we've got this one. So that's where the a, c, and e come from. And the reason why I set it equal to 0 is because we don't have an s to the 4th term up here. And I want this numerator to give me back the numerator that I started with. So all of these 4th degree terms should add up to 0. And then we do the same for the other powers. So s cubed, I've got 1, 2, 3, 4 of those, and that's where this, and that come from. And for the s cubed terms, right, the coefficient in front of the s cubed is 5. So that's why I set all of this equal to 5. And then we do the same for the s squared and the s in the constant term. So what you get is a system of 1, 2, 3, 4, 5 equations in 5 unknowns. And then you go through and try and solve it. So for me, I kind of said, well, this is the easiest equation to start with. That gives me b. Once I know that b is -1, that tells me that a should be 0. And then I just kind of went back through and solved for the other constants. Yeah, so this one probably took you a little bit of time. Yeah, so just watch out for that. On the exam, I'll explain this to you when we're taking it, just so it's clear, but you'll have some problems where, you know, the caution is on these problems, I'm sure you've come across it, is if you mess up these steps and you solve incorrectly for y of s, you might be left with something that would take you a whole lot of time to try and do partial fraction decomposition if it, you know, is a little bit messier than what I might have intended the problem to be. So to kind of help mitigate some of that, some of the problems I'll ask you to solve completely. So your answer should be y of t is equal to this. Some of the problems, the instructions are going to be just do the first 2 steps. Tell me what the Laplace transform of the solution is, and don't go beyond that step. And that intention is to make sure that if you've made a mistake at this point, that you then don't go and continue on and spend a whole lot of time on a partial fraction decomposition that might be really, really nasty. So just be sure you read things carefully. Which problems are you supposed to take all the way through the process? Which ones do you not need to do that? So there'll be some questions on the exam that just give you something like this. Well, not this one, because this one was hard. But like, there'll be some like this, which just say, give me the inverse Laplace transform. And in that sense, at least I know that you're spending time on finding the inverse Laplace transform of the right thing, which should not take you an infinite amount of time. That's always bad when an exam problem takes an infinite amount of time. Not a good written exam.
So this was one of my questions, and where I had gotten stuck is when you transfer over the s squared minus 4. I did not split that up. And so that's where I couldn't get the partial fraction to play nice.
Okay.
So for anyone else who didn't see that.
So that was on which part? Sorry, Kyle?
On B, but when you're transferring over your ys, s squared minus 4 to the right-hand side in the denominator. So you don't want to have any kind of powers within the parentheses when you're doing partial fraction. Is that correct?
So you mean as far as like the way that I took this and wrote it as s plus 2 times s minus 2.
Correct.
Yeah, you would want to try and factor it as much as possible, but not all things can be factored. So like in question 6, when you were doing some of these other ones, you know, like in part E, you wanted to do the inverse Laplace transform of this factored, so that process worked. Something like F, this didn't factor, so we weren't able to break that up, but you had to do this kind of process of sort of completing the square. So if you have a quadratic thing that doesn't factor over the reals, then this would be what you would do with that term. Okay, so I think that was the questions, at least on as far as the homework that you did for Monday. Yeah, so there were some questions about the review as well. So let's see, let's take a look at that. And let's see, so one of the questions on this was 6 and 8C. Yeah, so 6 was, this is one of these problems exactly where you're not required to find the inverse Laplace transform of y of s. So if you wanted to work on 6, just copy this. Then kind of the process here would be, well, first we take the Laplace transform. And we break up using properties L1 and L2. And then we use, you know, I think it's property L4, something like that, with the derivative. And so that would be s squared times the Laplace transform of y minus s times y0, which would be 3, minus y prime of 0, which is a minus 4. And then here we've got 2 times s y of s minus y of 0. And this one would give me 1 over s minus 2. Any questions about that part? That's kind of like the step 1 in this process. Now we want to solve for ys. And one caution that I'll just say, one of the common mistakes that students might do, or I might do, is to forget to distribute that 2 through everything. So this is 2 times the Laplace transform of y prime. So I want to distribute that to everything down here. So then we group our y primes, or excuse me, our y's together. Got that one, and that one. So that gives me s squared y of s minus 2s y of s minus y of s. And then I've got my other terms, this one, and this one. And that's, again, where I want to be sure I distribute that 2 to the minus 3 in there. So that gives us plus 10, I think. And so now that we've grouped things, we can pull out the common factor here of ys. Okay, notice we get over here the same characteristic equation we would get if we were trying to solve the homogeneous system. So that would give us that. And then we just divide everything. On the answer key, I might have added these fractions together and just wrote it as one fraction. But for this one, you don't need to do the third step. So it just says solve for y of s, but don't take the inverse Laplace transform of it. Any questions? I think there was another question about 8b, maybe. Does that sound right? Oh. Okay, so for this one, take the Laplace transform of both sides. I might just streamline this process a little bit, but let me know if you want me to slow down. So taking the Laplace transform of that, we would get s squared ys minus s times 0 minus a minus 1. Plus 2 times the Laplace transform of y prime, which would be this, minus 0, so I don't need that. And then I take the Laplace transform of the two things on the right side. 2 factorial is 2, so get that.
And then would it be s squared underneath 4?
No, so for this one, we just get a oh, sorry, I missed the t here. You're right, yeah. Thank you. Yeah, there's 4 plus t, so it would be 4 times the Laplace transform of t, which is 1 factorial over s squared, yeah. Okay, and then we can do some arranging. So one thing that when you're eventually going to need to go and take the inverse Laplace transform, sometimes it's nice to just have like to have y of s equals a fraction, so that we just need to do this partial fraction decomposition one time. So combining these, we would get 2 plus 4s over s cubed if I multiply this by s over s. And then on this side, we've got y of s times s squared plus 2s plus 2, and what's left over is a 1. So it just just to not skip any steps here, we could subtract the 1 from both sides, and then suck that into the fraction that we already have, put it over the common denominator, and now we can divide by so for anyone that might have gotten to this already, does that match what you've got at this stage? Anyone have any comments about that? And so this is a good one just to talk about how we might do the inverse of this, since that is asked on this part. And so now we've got a couple of things going on down here, which is interesting. So first thing is we have a repeated root. And second thing is this guy doesn't break up any further. So I can't factor this over the reals because this has imaginary roots. So if I'm doing the inverse Laplace transform, before I do that, I'm going to do some partial fraction decomposition. So these are going to be my factors that go into this common denominator. And now I need to have one of them for each of the repeated roots. So I'd have an s squared, and an s cubed. And for each of them, I just need a constant on top. Okay, whereas this one, that's a quadratic. It's not a repeated root. It can't be factored anymore. So for that one, I need to put a linear term over that. And so eventually, when you take the inverse Laplace transform to solve for y of t, then these things you'll be able to calculate the inverse of without too much difficulty, since they're from the table of common Laplace transforms. And for this piece, you're going to get these e to the whatever times sine and cosine terms, since this one, if you complete the square, you would have something like this on the bottom. So this is a tricky one because you need to do partial fraction decomposition as well as this complete the square sort of process. So from each of these terms up here, you're going to get power functions. These are like t to the n sorts of things. And from this one down here, you're going to get the e to the at cosine bt, e to the at sine bt stuff. Okay, any other questions? Yeah, I put some comments down about just looking at work, some things that we should talk about, and we've talked about all of them. So you guys had questions about them as well. So unless there are more questions, our time is over. I'm trying to drag it out. But thank you all then. You're welcome to stick around. We've got another 20 minutes or so. So if you do have some questions that are more individual, you're welcome to stick around. Just want to say thank you all for being such a really nice and fun class to work with. I am sorry that we did not get a chance to see each other in person, but I hope for those that will be around, I do get to see you at some point on campus when we're back there. But it was great meeting many of you. For those that are watching this on YouTube who weren't able to come, I enjoyed working with you too. Unfortunately, we didn't get to see you in here all that often. But good luck on your exams, on all of your finals. And I also just want to say that I'm a believer in the teacher-student relationship being a commitment for life, not for a semester. So if you do have any other questions down the line, please don't hesitate to reach out for me. Just because we might be done this semester doesn't mean we have nothing to do with each other anymore. So definitely feel free to reach out for me if you have any questions. But good luck on your exams, and I will see you all on Monday, same time, same Zoom link.
Thanks. Have a good weekend.
Thanks, too.
Thank you.
Yep, and I've got office hours tomorrow too if people have questions.